Okay, so now let's get started with our next keynote talk. I'm happy to introduce Professor Abhinav Gupta, who is an associate professor at the Robotics Institute, Carnegie Mellon University. His research focuses on scaling up learning by building self-supervised, lifelong, and interactive learning systems. Specifically, he is interested in how self-supervised systems can effectively use data to learn visual representation, common sense, and representation for actions in robots. Abhinav is a recipient of several awards, including IAPR 2020 J.K. Agarwal Prize, PAMI 2016 Young Researcher Award, ONR Young Investigator Award, Sloan Research Fellowship, Okawa Foundation Grant, Bosch Young Faculty Fellowship, YPO Fellowship, Ichkai Early Career Spotlight, ICRA Best Student Paper Award, and the ECCV Best Paper Runner-Up Award. His research has also been featured in Newsweek, BBC, Wall Street Journal, Wired, and Slashbot. So Abhinav today will be talking about continuous self-supervised learning and curiosity. Thank you for accepting our invitation, Abhinav. Yeah, I think you can start now.
Thank you for inviting me. Can you hear me? Just to confirm one time.
Yeah.
Okay. All right. Thanks for inviting me. And I'm really sorry that I could not make it in person. I was super excited to make it in person, but last minute changes. Okay. So I guess all of us know the story of this decade, right? We have made significant advances in AI thanks to deep neural networks, convolutional neural networks, whatever you want to call them. But if you think the learning paradigm, the way these networks are used for learning, the systems are learning, it still is quite narrow in scope. So how does a standard learning system work? So you first fix task. So if you are doing computer vision, you will fix categories for classification. If you are doing reinforcement learning, you fix an environment like Atari or whatever. You then label the data. So if you're doing classification, you label the data. If you are doing reinforcement learning, you engineer the rewards, or you can use the scorecard as the function, reward function, and so on. And then you perform supervised or reinforcement learning. And let's say this system works. Now you have a completely different problem. You change a completely new game to Doom or something, or you change the set of categories. Now you have to redo all these steps again. And you cannot use what you have learned in the past. Now compare this to how learning happens in the case of humans and animals. In the case of humans and animals, learning is completely task independent. Most of the learning that we are doing is self-supervised in nature. We are not learning our visual representations by categorizing mushrooms and dogs and so on. In fact, we are trying to somehow make sense of the world we live in. We are trying to understand what are the common sense rules of the world we live in and what happens when we do actions in the world we live in. This whole learning is kind of driven by curiosity and your own ability to understand more and more about the world. The main important point of driven by curiosity is that you're not learning from passive data that is being thrown at you. You're learning by your own active exploration. You do experiments in the world, and those experiments help you to learn a better world model of the world. And both these points, the task-independent nature of learning or the self-supervised nature of learning, and the whole learning being driven by curiosity, I argue leads to continuous and lifelong learning. Because you're doing task-independent learning, you can basically use all the data that you are gathering. So if you are in one environment or the next environment, even though the task might be changing, you are able to, because the learning is task independent, you're able to use all this data to contribute to this common model of the world that you are trying to learn about. But forget all these reasons. There's one reason why the current paradigm of labeling rewards or labeling images and engineering rewards is not going to work, because that is not scalable at all. So, for example, in the computer vision area, right? I mean, ImageNet was one of the biggest data sets, and that labeled 1 million bounding boxes in 5 years. Whereas the amount of images that are on Facebook or Google, they are huge. The billions are uploaded daily in some sense. When it comes to actions, when you're trying to engineer rewards, most of the papers that you see or most of the systems that you see are using only 1 to 2 tasks. And if you are doing it in simulation, you have millions of examples, but if you're doing it in a lab setting, like a real robot setting, you'll have a few thousand examples. Now compare this to the number of tasks a child can do. It's like thousands, and they use thousands of interactions daily in the real world. So it's clear that this whole labeling paradigm and engineering rewards paradigm will not scale up to the number of tasks or the number of categories, essentially. So my research has been to kind of scale up learning, to not just be confined to 1,000 categories or few 5 to 6 tasks at a task, that we are by building this task independent lifelong learning agents. And the keywords here are task independent and lifelong learning, essentially. And so what I believe is that you can scale up learning by having these two important categories of in your learning system. In a more uh, kind of simple sentences, in some sense, I want to build robots that will learn like babies, essentially, right? Because what I am arguing is that humans are learning in a task independent and lifelong manner, essentially. And so, with this goal in mind, in 2013, I started on this journey of saying, okay, let's try to build a system that can, lifelong learning system that can just build the world models or common sense models of the world, essentially. So in 2013, we actually built one of the first visual lifelong learning system that was, we called it NEAL. NEAL stands for Never Ending Image Learner. It was a computer program that ran 24 hours a day, 7 days a week. And it basically tried to just build the common sense model of the world. What NEAL essentially did was it basically downloaded images from the internet. Since these images were associated with text, it used the association between the text and images to learn the visual models of the nouns, for example, corolla and so on. It then used millions of unlabeled images that it has downloaded to identify objects in these millions of unlabeled corpus of the images, essentially. And by identifying objects in these corpuses, like cars, roads, and parking lots, and so on, it basically created correlations in the data and used those to figure out the common sense relationship. For example, NEAL was able to learn relationships like cars run on road, cars are found in parking lot, and so on. I want to highlight here that the whole goal of the NEAL was not to solve a task or anything like that. It was just trying to build a common sense repository of the world. And I want to call it semantic common sense repository, essentially. The basic underlying concept behind NEAL was that learning one thing improves the ability to learn the next. So you cannot try to learn all the categories at one shot. So if you want to learn a hard category like this, you have to go through step by step. You have to learn simple things first. For example, wheels. Then you will learn once you have learned wheels, you will use the relationship of wheels to learn about bikes. Once you have learned about bikes and wheels, then you will learn about motorbikes. And once you have learned all these three categories, then maybe you can understand this complex category, and so on. And NEAL was kind of, in my mind, a great success, right? Because for me, it ran for 2 years. It was able to generate 5 million labels. Some of the labels, sorry, the graphics are pretty hazy, but some of the labels that it generated was like Bean has 3 different meanings, Mr. Bean, Sean Bean, and Bean Food. Falcon has 3 different meanings. For example, the Falcon, the bird, Falcon, the bike, or Falcon, the car. And it was able to learn 20,000 common sense facts. For example, wheel is a part of a car, eye is a part of a baby, helicopters are found in airfield. And so these 20,000 facts were like high confidence, and there are a lot of low confidence facts also that it was trying to label, essentially. And it was able to learn models for 10,000 concepts in these 2 years. And it got a lot of fame as well at that point of time, because it was kind of for one of the first lifelong learning systems for vision, essentially. But after 2 years, we decided to stop running it continuously. We basically stopped the system because in some sense, I learned some lessons that if you have to build the next generation of lifelong learning system, this might not be the only way. We have to basically make some changes. And so there are 3 main lessons I learned by running the system for 2 years, essentially. So the first lesson I learned is that what I am labeling common sense as what NEAL was learning is kind of one kind of common sense. It's semantic common sense, which is trying to understand the hierarchy of objects and so on. But we also, when we are trying to learn the world models, we also want to understand the physical and functional common sense. And to learn physical and functional common sense, you cannot just download images from the internet and basically hope that you can learn things about gravity and containment, like one object can go into another and so on. What you need is some kind of ability of agents to do action, and you need some kind of embodiment, because physicality is very, very critical to learn the physical and functional common sense. Next, I also realized that there is a big factor about causality that needs to be learned when you're learning these big common sense models, essentially. And to learn causality, you need intervention and you need curiosity, right? I mean, we have heard from a lot of psychologists that babies are kind of acting as scientists. They basically come up with their experiments, and with these experiments, they learn about the causality. They come up with the experiment that if the gravity works, and if I leave these noodles down, they will fall and on the floor and so on. And so this idea of having intervention and having this curiosity, like ability to do your own experiments in the world, is kind of very, very critical to learn this dynamic common sense, which is a very important part of, or causal common sense, which is a very important part of this common sense repository or the world model that we want to build. And the last part is to really have a scalable lifelong learning system that is not going to be biased by the semantics. You need this task independent self supervision. You just in the current Neil system, it was still trying to use the nouns or the verbs as the categories essentially. And you, to really scale it up, to really understand the underlying concept, you have to go for this kind of self-supervised systems, which are going to be task independent, not driven by language or nouns or things anymore. And so with that goal in mind, in the next 2 or 3 years, I started going into more of these 3 pillars that I talked about. The first pillar being the self-supervised learning. So in 2015, we had a couple of self-supervised learning papers, which was for the first time where the performance of the self-supervised learning system was competitive to the supervised learning systems. They were not beating it at that point of time, but they basically came very close to supervised learning systems even at that point of time. For example, on the left is the example where we take out random 2 patches from the images, and we ask the network to predict their spatial layout. And by hiding the spatial layout, we are able to learn a good representation of pixels and so on. And on the right was a paper where we basically tracked object patches, and we tried to have their embedding similar because this is the same object in different viewpoints and so on. Then the second aspect we wanted to move towards was this whole idea of having embodied self-supervised systems. And so we basically created 2 embodied self-supervised learning systems. One was the self-supervised system for grasping. So here on the left is an example where the robot randomly tries to grasp object. If it is successful, the force sensor on the wrist measures the success and turns happy. And by collecting large amounts of data, we were able to learn a good model of grasping by just self-supervision, essentially. On the right is a drone example. On the right is a drone example where the drone crashed into thousands of objects, and it basically tried to learn a good model of drone navigation, essentially. And in 2019, 18 and 19, we started exploring more about the curiosity and to build the first hardware curious system. Here, the robot is just trying to do the experiments based on what it thinks is interesting to learn. Sometimes it pushes objects, sometimes it grasps object, and based on that, it basically tries to learn about the action model of the world. And since then, I would say that there has been a lot of work in the area of self-supervised learning. So I'm sure all of you have been tracking mask autoencoders, MOCO, and they are now, these systems are even beating the supervised systems when it comes to visual representation. Even in the embodied space, there has been a lot of large-scale self-supervised learning systems. And in the case of active exploration, there have been curiosity-based models and so on, which have really been on the forefront of exploration, essentially. But what I'm going to argue is that even though all these different areas were started off with the goal of having this lifelong learning, they actually lost that essence over time. Over time, it became more and more data set and task driven. In the spirit of having a next paper, in the spirit of beating the state of the art, we became more and more data set driven, and we actually lost this whole idea that self-supervised learning was not for data sets. It was for learning over the period of time without any labels and so on. And so this essence of lifelong learning was lost into all these areas, essentially. Just to give a few examples, for example, in self-supervised learning, as I was arguing, the whole premise of self-supervised learning is to get rid of these labeled data sets. We do not want to use labeled data sets. We want to use all the data that is being generated in the world, the unlimited amount of streaming data. Yet, all the self-supervised papers will train on ImageNet, which is human curated data, and only 1.3 million images. And that is kind of defeating the whole purpose of self-supervised learning. Like, why are we even doing self-supervised learning if we have to learn it on ImageNet only? Similarly, when it comes to curiosity or active exploration, like we are seeing these lots of interesting papers on curiosity and exploration. But all these papers first fix a task that they want to solve, a Mario or an Atari. And then once they fix a task, they go and try to do this exploration in a tabular rasa format. Like this is the first time agent is being born and it's trying to explore this Mario game or Atari game or whatever it wants to explore. On the other hand, the whole idea of exploration and the curiosity was that you will have some built prior experience of the world, and that drives your next set of experiments of what you want to do in this world and so on. Now, it's not as if these areas have just changed the lifelong learning essence. What I'm going to argue is that the whole field of lifelong learning and continual learning with agents has gone into this whole era of task driven, essentially. So one of the common paradigms in lifelong learning system that is used is you first fix n task and then you cycle through these tasks. Like you first get 1 million iterations of task 1, then you give 1 million trajectories of task 2, then you get 1 million trajectories of task 3, and you see how much you are forgetting and how much you are able to adapt to these new tasks and so on. What I am going to argue is that this is completely non-realistic. This is not how we are going to get data in the world. Our data is not going, there are going to be no well-defined task boundaries. There's going to be no opportunity to give 1 million examples of one task and so on. And so in some sense, what I would argue is that both the lifelong learning fields and the other two pillars that I was talking about, self-supervised learning and exploration, have gone into this whole task-driven mentality, which I think is wrong. And so we started with this goal of building this lifelong learning systems that are going to be scalable, task-independent, active, with these nice lofty goals of trying to build an agent that is going to learn like babies. We said our pillars are going to be self-supervised learning and curiosity, but everything has come crashing because everything is still data set or task driven, essentially. And so in this talk, I'm going to try to make this correction and try to say that, okay, can we now get out of this data set mentality and move towards more continuous self-supervised setup or the continuous exploration setup, essentially. And so essentially what I'm going to talk about is, in the first part, I'm going to talk about how we can view self-supervised learning from the lens of continual learning, essentially, right? We are going to not assume that we have a static data set that on which we want to do self-supervised learning. Instead, we are going to assume that we have infinite, dynamic, and continuously generated data. Now, if we are assuming continual self-supervised setup, some of the assumptions that all these self-supervised learning approaches, for example, IID data and everything, are going to change. You cannot create batches that are going to be IID anymore. And that kind of makes the whole SSL field, I'm going to show is that all the SSL, even the state-of-the-art SSL approaches are going to come crashing down as soon as you remove the IID approaches and IID assumptions and all this thing from them. And so what we are going to look into is a simple approach to give it a head start of how you can do lifelong continuous SSL. But I think there is a lot of scope in this area. We have to do a lot of more research to actually move away from dataset driven SSL to continuous SSL, essentially. Similarly, in the case of in the second part of exploration, I'm going to also move away from this idea of tabular rasa exploration, that you fix a task, then you start exploring the world. We are going to move away from that, and we are going to go to a more realistic setting where you learn how to explore from some environments, and then you go and start exploring a new environment, essentially. So you have to transfer exploration. You are not going to start tabula rasa in every environment whenever you are going to be tested. And if time permits, I might just briefly talk about that, how to actually bring this whole continuous SSL and the continuous exploration fields together. Because at the end of the day, agents are going to learn from both the passive data and the active data that they are doing experiments from. And so we need to bring, I think that one of the keys to successful lifelong learning is to have both learning from passive and active data together. And I'm going to talk about one of the ways that we have been focusing on, which is the large-scale pre-training, but there are multiple other approaches that I will just hint at of how we can bring these two fields together. Okay, so with that, let me start with the part one, which is moving away from dataset-driven self-supervised learning to more continuous self-supervised learning. So this is a paper that appears as an oral in ECCV, but I think I'm super excited about it, so I wanted to talk about it even right here. I mean, the first thing is, of course, we know that self-supervised learning has been making huge grounds in the last few years. I mean, I'm sure you have heard of SimClear, BYOL, MOCO, MAEs, mask autoencoders, and so on. And in fact, there has been so much excitement about self-supervised learning that in recent papers, you are seeing that self-supervised learning is even beating supervised counterparts in some sense, essentially. There are two components that we can argue have contributed to the success of SSL. First is this whole idea of augmentation invariance, like you augment images, you crop images, and you say they must have similar things. And the second thing which you have, if you closely notice, is that most of these new approaches that are coming, they're training more and more on the static data sets. Like initially, they used to be 50 epochs or 100 epochs. Now you see papers with 800 epochs and so on. So they are basically able to extract more and more juice out of these data sets, essentially. And so what we are asking this question is, have we achieved the goals of SSL, right? We started the whole field of SSL with the idea that we will not use data sets anymore. We believe that the era of data sets is over. We should be more trying to deploy learning in the wild. So we should be not using the labeled images. We should not be using human curated data sets. And if we can remove all of that, we can actually scale up for the first time to billions or trillions of images that are being uploaded on the web every day. And so have we achieved these goals with which the SSL kind of the whole field of self-supervised learning started? And the simple answer is no, because all the papers that you see in SSL, even the most state-of-the-art papers, are actually all being developed on ImageNet and tested on ImageNet. And what I'm going to argue is that this is just because we want to publish better numbers and so on. So in this spirit, we have actually forgotten the whole original spirit of SSL, that why we actually wanted to do SSL for itself. And I'm going to argue that the amount of data, if you want to use, is huge, right? I mean, and so there is no reason why you should be doing epochs over these data again and again. I mean, that's kind of, if there was a dearth of data, you should be doing epochs, which is the case in the case of labeled data. But when you are using unlabeled data, why do you want to see those images again and again when there's millions or billions of other images to see and so on? So in this part, what I want to explore is how can we deploy SSL in the wild, which is how can we learn from infinite, dynamic, and continuously generated data. And so there are three parts of it. First is we want to learn from infinite data. And so what that means is you cannot create data sets anymore. What that means is you cannot create these batches of IID data anymore. And you will only get to see data once as it's streaming, and maybe you will never get to see the same data point again, essentially. And so that's the first part of if you want to go towards continuous self-supervised learning. The second part of continuous self-supervised learning is that the data is not going to be IID anymore, right? If you are streaming data, videos, the frames are going to be related to each other. Even if you're not using the streaming data, let's say you are using the Instagram or whatever source of data, again, the data is not going to be IID because there is some hot topic going on, like elections or Olympics or whatever. And so the data is not going to be IID anymore. You are going to see lots of data of one type on one point of time, and then the data will change as based on what is hot or what is being discussed at that moment of time. And so the whole IID assumption will break down, and we will have more correlated data sources. And finally, we do know that as time progresses, the semantics that are non-stationary, like the semantics of the data changes, right? We might not have had cars in 1800s, but now in 1900s we'll have cars or planes and so on. So the semantic composition of the data set is going to change dramatically over time, and that has to be accounted for as well. And so these are the three big challenges if you're learning in a streaming format, if you're doing self-supervised learning in a streaming format, essentially. So let's look at these three challenges one by one and how conventional approaches work and what can be ways to fix the conventional approaches, essentially. So let's first start with infinite data. So just to remind, what is the difference between infinite data and so in the case of current way of epochs, you have a data set, you do a training, then you shuffle the data again, and then you do next epoch of training, then you shuffle the data again, you do another epoch of training, and so on. By doing the shuffling of data, you are basically able to see the same data multiple times, and you're able to create these batches that are going to be IID essentially. Now, on the other hand, in the case of streaming, you will have one streaming source, and the data will come from the streaming source one by one. And if because this is infinite and continuous source of streaming data, you can store it, but there's only a limited storing capability. You cannot just store every data set, every data point, and so you cannot really go back and do the whole epoch. And it might not even be worth doing an epoch, essentially, because as I'm arguing that maybe the new data is more worth seeing than seeing the same data again and again and again. And to adapt this conventional SSL approaches, what we did was, this was the first simple part, right? I mean, maybe what we can do is we can introduce some kind of replay buffers. These replay buffers have been already used in RL as well. And so we said, okay, can we use some replay buffers from the streaming source? So we'll maintain some replay buffers of the data that we have. Then given the replay buffer, we'll train multiple times from that. So this is kind of acting as a static data set for a moment. We train it, but then when the new data comes in, we remove some of the data from the buffer, and then we train again multiple times from that buffer, and so on. So this has two benefits of going this way essentially. First, while you're waiting for streaming data to send new streaming source to send new data, you can do multiple epochs on the same data. That's that one thing. So it can kind of treat it as a static data set essentially if you want to. But more importantly, this kind of decouples the streaming from the SSL training, and you can basically have a more efficient learning in some sense. And so we did that and wanted to compare actually how this compares to the one pass SSL and so on. So these on the left, we are showing the accuracy on the ImageNet. On the bottom axis, x-axis, we have these different data set size, 20 million, 5 million, and 1 million flicker. And we are basically going to run multiple epochs essentially. So if you do conventional SSL where the data is streaming, so you can only look at the data once. You are not creating replay buffers. You are not creating multiple training over the replay buffers. You're just doing one round of training as the data comes through and you're going through. You can see already, even with the 200 times data, you have basically the performance is falling dramatically, essentially. Like Flickr 1 million, the performance is just less than 10%. With this whole buffer like way of doing it, where you can actually create a static data set for a moment of time, then run multiple epochs onto it. In the meantime, the next thing comes, you can actually improve the performance a lot. And compared to the epoch-based SSL, where you are actually going to treat the whole data set as one thing and you run 200 epochs on it, this is actually very close. So this whole buffer thing where the buffer size is as small as 16,000 examples, you can actually mimic the performance of epoch-based approaches essentially. And so that's a good start. So at least we know that adapting to infinite data might not be that hard essentially. But the other problems are going to be even much more serious. So for example, the second problem that we want to handle in the continuous self-supervised learning is a correlated data source, that the data source is not going to be IID anymore. The data is not going to be IID anymore if you are creating these batches, because the close-by frames or the close-by data points are going to be much more related. And I already talked about how this can happen, like in a video, of course. Nearby frames are going to be correlated. They're not going to be independent. And in the case of web uploads, there is this theme going on of what people are trying to upload, like Olympics or elections and so on. And that kind of correlates these data sources essentially. To adapt our approach to this, what we did was we basically, when we are adding to buffer, instead of adding in a first in, first out way, we are going to match the distances of each example in the buffer and remove only the redundant examples. We are not going to remove the first example that came in and so on. And with this simple approach, so you first have a streaming source, you create a replay buffer, then you find out the most closely related examples. For example, anchor and the ship are closely related. Then the two apples are closely related, so we'll drop those because they are the most redundant in the feature space. Then we'll find more examples to create a replay buffer. And then we'll do redo training and then drop again similar examples and so on. So this is going to be our minimum redundancy replay buffer that we actually created for this experiment. And just in the case of what happens in terms of approaches. So these are the two data sets. So the first two are kinetics, like these are YouTube videos with a frame per second of 8 or a frame per second of 2. They're not related. The third one is the data set called Krishna Cam is my favorite data set in the sense that it is the life of one grad student who wore this egocentric camera, and he wore it for I think 6 months of his life. And so this is kind of very much like the kind of data an agent would see essentially. And we want to do self-supervised learning on this data. So it's going to be highly correlated in time, but it can also be correlated over the long ranges of time. And as you can see, the conventional SSL and even the simple buffered SSL, the first in, first out, they kind of come crashing down in the case of Krishna Cam or when you have high frame rate for videos as well. But with this minimum redundancy buffer, it kind of improves the performance dramatically. And it comes kind of, I would say, quite close to as if you were treating this as decoded, like you will take all the data in, you will shuffle, you will create batches, and based on that, you will send it to the thing. So in some sense, by having this minimum redundancy buffer, you kind of match the performance of the shuffling. It does not exactly reach there, but it comes very close to it essentially. The third challenge of I would say continuous self-supervised learning is the whole lifelong is the whole non-stationary semantics aspect, right? I mean, as I was arguing that um, you are basically going, the distribution of the semantics are going to change over a period of time. So it could be at a different scale, like over the period of years, new objects are appearing. But even at the small periods, like for example, you're at home, you're going to see indoor objects, then you're on the way to work, you're going to see cars and buildings, and then you're at the grocery store, you're going to see more grocery items and so on. So the distribution is changing as we are getting the data, moving the data along. So the question is, as you get new and new data, are we going to forget like the old categories, or how is the performance going to be on these old categories and so on? And so we wanted to test that if we cannot have ImageNet and we can shuffle all the categories and so on. Instead, we have these kind of streaming way of like first having home categories, then having outdoor categories, then having grocery categories. How would, and we do self-supervised learning on these kind of data, like what would the performance be? And so to do that, we basically took ImageNet 21K, we divided into 4 different parts. And so now there are 4 different data sets, D1 to D4. And we are going to train on these data sets one by one. So we are going to train on D1 first, which has one set of semantic categories. Then we are going to train on D2 and test on D1. Then you're going to train on D. This is kind of very similar to the task setup that people do like cyclically. We are not doing any cycle here, but we are just saying that the distribution is going to change of categories because D1, D2, D3, D4 have different semantic categories essentially. And so this is how we are going to train. And we are going to test at each point of time, like at each stage, we are going to test on all the 4 data sets, like what is the performance on D1, D2, and D3 and D4. So if it was perfect, like if it was transferring from D1 from D2 and there was no forgetting and so on, you would expect the performance to keep on increasing, right? I mean, after D1, your performance would be something on, and then after D2, your performance increases. So this is testing on D2. When you train on D2, you would expect a much higher performance change. But when you train on D3, maybe the performance will not change, but hopefully you will not forget D2. And so the performance will be very, very similar. Maybe D4 is more correlated with D2, so you will see much better performance, like some performance gain and so on. So this is what you would expect if your continuous SSL system was working perfectly. But in reality, what we saw is that if you are using a self-supervised learning system with this kind of data distribution, after D1, of course, it's not doing very good. But once it learns on D2, the performance improves a lot because we are testing on D2 after training on D2. But as soon as you train on D3, there's a forgetting part that happens immediately. And then with D4, even further more forgetting happens. And so the performance falls even further. If you try the first in, first out buffer, that also does not seem to have any benefit here. But the minimum redundancy buffer, which is maintaining examples from the past, which are very different examples, seems to help this setup, and it kind of improves the performance a bit. But again, as I want to say, all the 3 challenges, what I am presenting is a very simple way of handling with these buffers and minimum redundancy and so on. But there is a lot more work to be done here, essentially. And so for me, the take-home message is not there's a minimum redundancy buffer or there's this kind of approach and so on. But the main point I was trying to make here is that it's time to start looking beyond this ImageNet for when we are doing self-supervised learning, because that is what not self-supervised learning was made for. And when you go to this setup of continuous SSL, the conventional SSL approaches try to kind of break down because all the assumptions break down. We presented one approach of replay buffers, which might help a little bit, but they still are, as I said, a long, long way to go here to reduce forgetting and all those other aspects itself. Okay, so that was the first part where we are trying to recast self-supervised learning to more continuous self-supervised learning. In the second part, I want to do the similar with exploration, right? We want to move away from tabula rasa exploration, where agent is born and it has suddenly got to learn about this world with no prior experience, to more transfer exploration. We are going to always assume that the agent has some prior information from prior worlds, and now you have to go and adapt yourself into the new world, essentially. And so this is a work that appeared in NeurIPS 2021, in case you want to read the paper. Okay, so the way we have been doing mostly exploration is in the field of RL is task-centric, right? I mean, extrinsic, like one of the ways we have been doing exploration is task-centric, where you define the task and then there is some way we have rewards, which is going to drive the exploration essentially. And so in the case of a tie, these might be the score in the game and so on. Recently, there has been a lot of work on agent-centric exploration as well. Like the agent has its own curiosity and it wants to see newer and newer states, or it wants to have it has a predictive model, and wherever predictive model fails, you want to explore more of that area essentially. And but if you look at both these setups of task-centric or agent-centric, and you look at all the papers, whenever the exploration starts, it always starts tabula rasa. Like when the environment is, you choose an environment and then you start exploration with a scratch model at right that point of time. And so what we are going to argue is that this is not how exploration happens in the case of humans. We never are learning from one environment. First, we are learning from multiple environments at the same time. For some time, you are at home, then you might go to playground, then you might go to your preschool, then you might go to your kitchen. And so the different environments are contributing to building up your exploration policy, essentially. But more importantly, we are not doing exploration in one and then completely forgetting and restarting our exploration policy, like retraining our exploration policy and so on. What is more critical is whatever you have learned from these past environments should help you to transfer something into the new environments. You should be able to learn. It should improve your exploration as you're going to newer and newer environment. And this is kind of related to this whole idea of lifelong exploration, right? I mean, you never stop exploring. You are using your past experience to explore more and more every time into the newer and newer setup. So what we want to do is we want to build agents that can learn how to explore from multiple environments, but we also want agents that can learn how to explore by playing in some environments, and then when going to new environments, they transfer some information from this old environments to the new environments. But of course, the main critical question is what do you transfer, right? If you have like two environments, let's say a simple, these kind of grid, mini grid examples. Let's say you want to learn exploration on the left and you want to transfer it to the right. What do you transfer? One can argue that maybe we can transfer the agent's model, the agent's model of the world, right? So if the agent has learned how to explore, how to interact with keys, the next time when it goes to a new environment, it will not interact with the keys because it already knows, it has a very good predictive model of keys, so it will not interact with the keys. But that would be actually bad if we followed that as an approach, right? Because we need keys to find the newer objects, newer curious objects, and so on. So in this work, we actually introduced the basic idea that some objects are just naturally attractive. Like you are naturally attracted to some objects and to interact with. So for example, let me think you are going in a new room and there's a red button in the room. Even though you might have pressed all the different kinds of red buttons in your life, when you see a red button, there's this inherent feel that you want to press it and see what happens. Or similarly, when you see very textured surface, you might know all the knowledge of how textured surface feel like, but if there's a textured surface, you still want to go and touch it. It's like the inherent desire in humans to go and interact with those objects, right? So similarly, we want agents that have desire to just interact with a few objects. These objects are the objects that are going to bring changes into the world and so on. So we want to capture this interestingness of the property. Now, I want to highlight that this is an environment property. Till now, we have been building agent models, like what has agent seen. So if you are doing count-based exploration, you're modeling what has agent seen, what different states agent has seen, and so on. But interestingness, capturing this interestingness of object is an environment property. And so this is an environment-centered component of our exploration. And it promotes some interaction or some changes into the environment. And so those are the kind of objects which are going to be interesting, and we want to actually explore in that area, irrespective of whether we have done it in the past or we might have a very good model of it and so on. And so in this work, we basically had this three aspects. So first, we argued that we need to move away from tabula rasa exploration to learning to explore. We want to learn how to explore and then transfer the exploration to new environments and so on. So we proposed some benchmarks and metrics of how to explore, how to measure how are you transferring exploration from some environments to the new environments that you are seeing. And then we are going to propose an approach of how to transfer from one environment to another. And the way we are going to do it is we are going to decouple the two components of exploration, which is agent-centric and environment-centric. Just to remind again, agent-centric is the component which actually tells you to go to newer states. It's your curiosity to go to newer and newer states, essentially. And environment-centric component is you want to interact with objects that will create some big changes in the environment. You just like that as a way to interact in the world. And so these are the two components that we are going to have. And based on these components, we are going to propose a new exploration transfer approach, which is change-based exploration transfer. Okay, so let me first explain the setup of how we are going to evaluate, or like the benchmark setup, how this is going to be done. So initially, you're going to be given n environments. These n environments, you have to learn, you have to explore these n environments with any policy, and you have to basically learn an exploration policy from these n environments. Essentially, we are going to we are going to propose an intrinsic reward that helps you to learn a good exploration policy from these n environments. But at the test time or transfer exploration time, you are now certain, whatever you have learned in the exploration policy you have learned from this environment, you are now going to transfer to a completely new environment that you have not seen before. And so you are going to use the exploration policy that you have learned to explore the new environment. Now you might or might not know the task in this new environment. And based on, if you know the task, you will see how good you can learn a new task policy. So exploration policy is going to be different from the task policy that you're going to learn. Exploration policy is just going to be to help you generate new trajectories, and you are going to learn a task policy. And the idea is, if you have learned a good exploration policy, you will have learn a task policy faster. On the other hand, if your exploration policy is bad, it's not transferring, then you will take much more amount of iterations or trajectories to learn a good task specific policy, essentially. And we are going to, so if we train from 3 environments, you're going to test on 10 new environments, essentially. And so these 10 will be completely different, essentially. And the approach that we are proposing is this CBET approach, which has going to transfer into like agent-centric component and the environment-centric component. So this CBET has 2 different terms in the reward function when we are trying to learn an exploration policy. The first one is the simple state count which is the agent-centric component. So this kind of tells you to go and visit newer and newer states. So if you're let's say you have been building your count models from the 3 environments on which you're learning to explore. If you see a new environment and there's something completely new in that new environment, you should go and try to explore it. So that's what this will promote. That even if you might, if you've not seen any object or anything in this past training environments and you see something completely new, this is going to promote you to go and try to learn, try to explore that new thing that you see. But apart from that, we will also promote things that create very rare changes or big changes, essentially. And so this is a count of the changes that have been created in the environment. And so again, the idea is if some interaction creates a change that is very rare or big, you go and try to explore those kind of interactions as well. Of course, this kind of setup really suffers from this whole idea that as you explore more and more and more, let's say millions or billions of things, the counts grow and reward vanishes. So we have this random resets, which is at any random point of time, you reset all the counts to make sure that the rewards do not go to completely vanish itself. And so for the benchmark, we have 2 different benchmarks that we are going to run here. The first one is the mini grid benchmark. In the mini grid, we have 10 different environments. We are going to train on the first 3 and then test on our transfer to all the 10 different environments. In the habitat, we have 8 different environments. We are going to train on, we are first going to see how this works on one apartment only, and then we are going to see how transfer from apartment 0 to works to all other different apartments in terms of exploration itself. Okay, so here are the results of how this works. So again, as just to remind you, we train on the first 3, and then we transfer to all the 10. We just check the performance on all the 10. Now, to measure the success, at the first case, we are not really having any reward, like any external task. We just want to see how many times do you reach a goal state. Even though the reward, like we don't have any extrinsic rewards and so on, but we know what are the interesting states in these things. And what we want to explore is, if you're just using exploration policy, how quickly or how many times will you reach those interesting states? That will help you learn about the task if the task was there. And so this kind of keeps your measurement separate from external reward-based like task policy learning, essentially. All you're checking is how good your exploration policies can reach different goal states and so on. And so as you can see, the simple count-based stuff works really good for simple setups. And but the right-hand side, which is the much harder setup, these are the setups of the multi-room, obstructed maze, like these 3 obstructed maze and blocked unlock pickup. That's where the simple count-based approach fails, but CBET works actually pretty good because it actually wants to it uses this in a multiple room setup or in a bigger room setup. You have to do multiple steps to reach to the interesting states. And because CBET has this inherent component of trying to interact with these interesting objects, it goes on towards and it tries to interact with those interesting objects and so on. And so you can see the performances go to there. Then we also try to um, adapt to the task. So now let's say you are using this exploration policy and you have extrinsic reward and you want to see how good of a task policy you learn. And so on the bottom is when there is no transfer. If you're directly learning in this environment from the extrinsic reward, these are the kind of performances that you will get on the 3 different rooms. But if you use the exploration policy that we have learned from the 3 other setups, you can see you can learn much faster than you would learn if you were actually starting tabula rasa. So I mean, this is kind of an obvious result that you will do better than tabula rasa, that because your tabula rasa exploration knows nothing, whereas here your exploration already knows something interesting. But for another interesting point to note here is that the blue line, which is the CBET, is working much faster than the count or any other ride or any other exploration approaches that are there essentially. And so it is able to transfer some interesting components from the earlier environments to the new environments in this setup. On habitat also, we tried, and again, CBET works really good. Here's the kind of coverage, but this is kind of the more interesting setup where CBET, so we train on the first, we train on the apartment 0 and then we transfer to all other apartments. And you can see that CBET has the best coverage of exploration as compared to any other like ride or count based approaches and so on. The CBET has really good exploration that it was able to transfer from one apartment to all other apartments essentially. Okay, so I mean the take home message is for me is simple, right? I mean CBET or no CBET, it's fine. I mean I'm sure people will come up with more approaches for transferring exploration, but we have to remember exploration is a lifelong learning problem. It's not exploration in an environment given a task. We should move away from this tabula rasa exploration to more exploration as a lifelong learning problem. And we should focus more on the setup of you have some environments where you will learn how to explore, and then you have to go and transfer to the new environments and see if you can explore faster and so on. And this continuous notion of exploration and the continuous notion of curiosity is very, very critical for building this lifelong learning systems that we want to build in the future. Okay, so since it's 3:18, I mean, I don't have too much time. I'll leave some time for questions. I will just quickly try to wrap up my third part. So in the third part, I wanted to talk about how agents learn from both active like data and the passive data, and both active and passive data are to be critical. So while we have seen significant advances in like self-supervised learning and vision and so on, what I am going to argue is that hardly anything transfers when it comes to any RL or robotics experiments that we do. There's a huge gap between computer vision as a field trying to do self-supervised learning and then people trying to do RL from pixels and so on. I mean, ideally, you would think that all these better representations that computer vision people are learning should transfer to RL. And so they should start from pre-trained representations and so on and so forth. But it never happens. And so what I want to explore is, whilst there's a big gap between passive learning, like learning from internet data, it could be egocentric or whatever, and active learning, this idea that agents are learning in the world. Even though they're learning from pixels, there's still a huge gap between the two fields. Nothing transfers from computer vision to this or the other way around, essentially. And so I want to bridge this gap between computer vision and RL and basically bring these two fields closer in some ways. And so there are 3 ways I feel it could transfer. Like if you're learning something from passive data, it can transfer to active data. The first is the simple way, which is the visual representation way. I'm going to learn such a good representation from my MOCO or autoencoder or mask autoencoder that whenever you want to do your experiments with robots or something, you should start with my network rather than starting from scratch or ImageNet model or whatever. The second is you learn some kind of dynamics model from the passive data and then somehow transfer it to the newer world. And a third one, which is kind of my favorite, recently I've been looking into it, but I'm not talking about today, but is to learn some interestingness of the the world from the passive data, like, oh, microwaves are interesting to explore. And now the exploration is going to be guided by the all the passive data that you have seen, and will help you to learn faster about the new world that you're going to be sitting in. In this talk, I quickly want to highlight the visual representation aspect. That can we actually make the visual representation that we are learning in computer vision work in the field of RL and exploration, like all the setups that we have been seeing and so on. And it is kind of surprising, right? I mean, if you think of ImageNet model or the SSL models and so on, they have all worked seamlessly in all the computer vision tasks. In computer vision, you train, you have a pre-trained model, and whenever you have to do a new model, like new task, you start with that pre-trained model and then you fine-tune it. But somehow these models have never transferred to control problems. And so what we wanted to explore was, is there something special about the control problems that they are not transferring, or did we get something wrong when we are transferring, essentially when we are transferring from this pre-trained models to the new control problems. And the setup we are using is the imitation learning setup. So we have a pre-trained representation. We will collect few imitation learning like demonstrations, and then we will learn the policy from these demonstrations with these pre-trained representations. And we evaluated on the whole suite of tasks, from habitat to dexterous manipulation to full kitchen environments and deep mind control suite as well. And we wanted to show that starting with the not using a Scratch or not even using ImageNet is the best. There's something else basically out there, or how to make it work essentially. And so, since I don't have too much time, that I'll just give the summary of the results essentially, is that what we found that the tasks like habitat, you can use the ImageNet models or self-supervised models. So self-supervised models work better than supervised. That's the first thing. And frozen pre-trained representations work better than starting from scratch or end-to-end learning or random features and so on. In habitat, in fact, it turns out that if you are using these representations from ImageNet or Moco or whatever, they actually work even better than the state vectors in some sense, because it's hard to capture state vectors of that kind of a scene, whereas the image captures the whole thing. But what about the manipulation stuff? Why hasn't this thing transferred in manipulation? And so it turns out that whenever everyone wants to transfer from ImageNet or self-supervised learning, they always take the layer 5, the last layer feature, and say, oh, they are not working for manipulation and so on. But what we have to realize is that deep learning, I mean, we are doing learning hierarchy of features. For manipulation, maybe the high-level features are not the way to work. And that is exactly what we learned out, that early layer features, like layer 3 features, are much better for manipulation. So instead of transferring layer 5 or layer 7 features, if you transfer early layer features, they actually work very good for even this manipulation task and so on. So in some sense, what we were able to do was build a hierarchy of features. And in the paper, we talk about how you can have multiple layer features into one common features, and then you can beat all the approaches. And you can actually just use this model as a starting point for any RL-based approaches that you want to do. So this could be a starting point for your pixel-based representation, and it will definitely work better than a end-to-end learning. And even in some cases, it comes very close to state vectors. So if you're learning from state vectors, you should just try this first, because this might actually make learning for pixels work as well. In last 1 minute, I want to highlight the paper that we have on Wednesday, which is CORA, a platform for continual reinforcement learning objects. Since this is a presentation on Wednesday, I will not go into detail, but the whole idea is that unlike vision and NLP, where there are lots of libraries, continual learning suffers from this whole entry barrier. We do not know the task, or the tasks are sometimes ridiculous, like Atari, and not at all like household robotics and so on. There are no publicly available baselines. So even if there are Atari results, it's hard to confirm whether what approaches would work and like what are the hyperparameters that would work. And so there are no publicly available code for the continual learning baselines like EWC or progress and compress. The metrics are sometimes too many or incomprehensible or something like that. So overall, it creates a whole high entry to barrier in whole continual learning field, unlike other areas. And so CORA is a way where we are actually having it's like a one-stop shop. You'll have all the baselines, like lots of baselines implemented. You have lots of metrics, and you have multiple benchmarks, from robotic style benchmarks to Atari and everything. We have confirmed the baseline results on Atari. We match all the performances, so you don't have to worry about the right implementation and so on and so forth. Just to highlight, this is on Wednesday oral session, so please definitely attend. All right, with that I'll end.
Okay, so if you have questions, you can come to the front mic, but I'm going to start with one of the from the remote participants. So the question is, okay, super interesting work. Have you looked at the failure modes of your CBET model? For instance, does it get stuck in noisy TV environments, or does it develop compulsive addictive behaviors?
Right. So actually, this is a very interesting question. We did observe that if there are lots of interesting objects, so in a scene, then it would get into this notion of trying to interact with a lot of interesting objects and so on. So that was, I would say, one of the, not the failure modes, but a mode where it would not perform, like if there are lots of keys and lots of other interesting like doors and so on. It would try to interact with them a lot more, and so it will slower the speed of exploration a little bit. The TV, noisy TV one, I've not. We did not try it here, but I mean, like whether it will get stuck or not. But I mean, thinking about it, I mean, because we have the interactive part of it. So if it was a count based, maybe it will. If yeah, I mean, I think the resets might help it a bit. But I mean, yeah, we have not tried the TV ones whether it gets stuck or not. But that would be an interesting thing to try.
Okay, there's a question from the auditorium.
Hi, so my question is on the self-supervised learning part of the talk. So the way you describe your lifelong SSL setting, I feel that maybe monitoring online performance or anytime performance on the current data distribution might be potentially more interesting than looking at performance on the held out test set. So my question is, did you look into doing so, and do you think that replay still offers gain in this setting?
Yeah, I mean, I think that's a great suggestion. And in fact, I would say the last setup where we are trying to do, let me go to that slide. 1 second. So in this setup that we are trying to do, we are actually trying to do as the distribution is changing, we are still evaluating on all the distributions held out really. So, or you can think of it as you keep evaluating on D2 when you're learning on D2, then you keep evaluating D3 when you're evaluating D3 and so on. So I feel like this comes very close to what you are proposing, where we are actually evaluating on all the data sets at all given instant of time. We are not just evaluating on held out data in this setup. Yeah, I mean, so I feel like, I mean, the performance, mine, as far as I think, I mean, it should be very similar behavior. Like held out data would do a very similar behavior as what I'm talking about, but maybe I'm wrong. I mean, at least thinking about it at the first shot, it seems like held out data is kind of similar, because in some sense, the new data that you are seeing this on online way is always held out data when you're evaluating on. So to me, it will behave similar, but I might be wrong.
Okay, thank you.
Hi, thank you for your talk. I also a question about SSL. You said one of the limitations of current SSL method is that they are trained on like pre-selected datasets such as ImageNet, and it would be better to train on the whole internet. But if we don't really know what is the data like inside the internet, how can we trust like the outcome of the training? To which extent that the concept of garbage in, garbage out applies here, could apply here?
Right. I mean, to me, actually, I was not saying that you should learn from the whole internet. That is one suggestion. But even if, let's say I want to deploy this SSL onto an agent, let's say I build a robot tomorrow and I want to say, oh, robot, you can go and learn your representation from SSL. All these problems that I talked about will sustain on that robot agent as well, because the robot is living for infinite amount of time, so it will be infinite data. It's going to observe like the correlated data set, so it's going to be correlated data sources, and lifelong learning. The distribution of objects is going to change. So I am arguing either from the internet, or if you're learning on an agent, some kind of representation. In both those cases, there is no concept of a data set essentially. And so the current SSL approaches, the way they are actually being formulated on a worked on a static data sets and so on, it's not going to work, because if you are deploying it on an agent, the agent will not have those data set style things at all and so on. Now, in terms of deploying on the rest of the internet and so on, I feel like a good SSL approach should be able to tackle the semantic drifts and so on as well, right? I mean, I think what you're saying is garbage in, garbage out kind of setup is that internet will have all different kinds of data as well. A good a good SSL approach should handle semantic drifts or whatever drifts that can happen from the garbage data as well. And I think this is one of the problems of lifelong learning itself. And I think it will be cool. I mean, in some sense, I feel it will be better to actually get drift and not work, so that we can actually learn about how to handle drifts and so on in real life. Then just because you don't want to handle the hard problem of drift, you don't want to do the. So what I am arguing is, let's tackle the hard problem for which SSL was made for, to do drifts, handle drifts, and so on. So if the drift happens, then we have some interesting work to do on multimodal learning, right? Because drifts can always be avoided by multimodality. Like audio can help you avoid the drift of vision, vision can help you avoid the drift of audio. And there'll be much more interesting fields that will open up if those drifts happen and so on. So to me, again, the better area of research or better area of which is so underexplored and should be explored more is this area of learning from the wild, rather than just trying to get a better number on ImageNet data, which I feel is totally kind of worthless at this point.
Okay, one last question. Okay, so I think there was one question in the chat. Like, oh, there's actually a question here. Maybe we'll finish with this.
I know.
Oh, you're the next speaker. Okay, so then maybe I'll do the last question. So the question is, more generally speaking, do you see particular failure modes that agents with good inductive biases for lifelong learning will necessarily or inevitably have?
I feel like I think I kind of answered this. I mean, like, for example, the failure modes that I was talking about, like especially in the case of seabed, the interestingness will transfer, and that kind of can sometimes become failure modes and so on. But by decoupling the two, I feel like you can handle the two aspects. You are still giving enough importance to curiosity or visiting new states and so on, so you can actually overcome those failure modes essentially. But yeah, I mean, I think generally I feel like whatever you are trying to train on in the previous environments, and if that doesn't work in the new environment, you will have this drift essentially. Like, it's the same idea of the drifts essentially, because if the previous data doesn't match, if the new distribution doesn't match the previous distributions, you are going to have some issues. And recognizing those drifts and handling those drifts is a critical issue, which I think is probably what this conference is all about, right? I mean, trying to figure out where drifts happen and trying to figure out how to handle those drifts when the distribution changes, essentially.
Okay, thank you. Okay, let's thank the speaker once again. Thank you.